we're going to cover the integrator AI and demonstrate how we've utilized LiDAR to achieve some of the things I've talked about in the previous slides. To start, we'll cover the integrator AI, a product that Blue Brand pioneered. We'll get you acquainted with what it is and what it does. Then we'll dive into the details of the transportation fusion concept we came up with that summarize the purpose of our product. After that, we'll show you how we got LiDAR into the transportation space and what we managed to do with it so far. Then we'll show you some of the LiDAR application that we've got deployed now to see what that looks like. Lastly, we'll give you a peek at some of the novel concepts and features that we have coming up, which really push the use of LiDAR and transportation fusion to the edge. So what is the integrator AI? It's a software solution that runs in the traffic cabinet and orchestrates transportation fusion. I'll explain what transportation fusion is in the next slide. Then we'll revisit this definition and it'll make more sense. For now, let's continue. It connects to all kinds of transportation devices through drivers and interfaces. I'm talking about different sensors, traffic signals, dynamic message signs, connected vehicle radios, contact closure and relay devices, agency service, and control circuits, just to name a few. If it's part of the infrastructure, we probably connect to it, or at least have the capability to add support to connect to it. We do this through our driver system, which are plugins that allow us to connect and control to all different kinds of products that are out there. Whether it's old, new, follows a standard, or completely proprietary, our drivers can bring in support for it. Interfaces are instances of the drivers, which facilitate individual connections to each of the devices. We let you create as many interfaces as you want, which is a critical component in achieving transportation fusion. The more we're connected to, the more things we can do. It also has apps, which are specialized algorithms. Think of them like apps on your phone. Each app you have serves a specific purpose. The same concept here, but these are focused on solving transportation problems. Just like drivers, these are also plugins, so we can easily add more down the road as new use cases, initiatives, or needs come up. Apps can provide specialized control over devices or just collect and generate analytics. They have full access and control over any device connected to the integrator. Ultimately, apps are what allow us to achieve transportation fusion. It also has an API that abstracts control and monitoring of connected devices. Imagine you have a mix of products out there and you'd like to deploy services that needs to put in a call to, say, for example, detector channel 25 for some reason. The way to do that will differ for site A and site B because they have different controllers. You would need to be aware of what product was deployed at each site while also having algorithms capable of communicating to each product in their supported way to place that call on detector 25. This is a tough task, especially considering some of these systems can be quite complex and hard to use, and they're all different. This is the problem that our API solves. Connect the device to our product, and now you can use the same unified API to control and monitor it no matter what product it is. Think of it as a simplified gateway to control any deployed product without having to know what or how the product works. The next point gets asked a lot, so we like to make it pretty clear. There is no cloud component to the integrator. It runs independently at each site without the need of any external support. We felt this was an important trait for a component running critical infrastructure. When things go wrong, like network outages, we keep operating. Another important trait we wanted to have was working with both old and new technology. Agencies have all kinds of equipment deployed, and some of it's pretty old. This is problematic when you want to adopt some new tech. The integrator lets you integrate the old with the new. We had a deployment where we were running an old TS1 signal with LiDAR. I think this deployment really highlighted our ability to bridge that technology gap. The integrator prevents technology from becoming obsolete too quickly. Since we can facilitate that interaction between old and new products, we can keep them in service for much longer. New detection systems come out, no problem, we'll just add a driver to support it. New algorithms to run stop bars, no problem, we'll just update our app to support it. With this kind of extensibility, it's really hard to become obsolete. Next, we're not locked to one or two products and use cases. We're designed to work with as many products as possible. We don't want to limit what we can achieve by picking only specific products. We also don't want agencies to get stuck in vendor lock, especially when they already have equipment deployed. Instead, agencies can pick the products they want to use, and we just add support for them. Lastly, we're designed to grow with agencies and technology. Design of the integrator was deliberately crafted to ensure we can just keep extending it over time. As new technology comes out, we just add new plugins for support. As new use cases and initiatives come out, we just add in plugins to support them. We want the integrator to continue to deliver value as technology advances, society progresses, and agencies grow. So let's talk about transportation fusion. Starting with data fusion, a concept that US DOT has been trying to get agencies to adopt. If you're not familiar with what data fusion means, here's a quick example. Imagine you want to gather analytics on jaywalkers. The first thing you need to consider is what kind of information is needed to detect jaywalking. First, you'll need to know where the pedestrians are. Then you'll need to know what state the ped indication is in. But there isn't a single source we can use that provides both of those pieces of information. So instead, we need to get that information from a sensor that tracks pedestrians and a traffic signal, which tells us the state the peds are in. Combining, aka fusing, these two data sources lets us detect if a jaywalking event is happening or has happened if analyzing historical data. That is data fusion. Transportation fusion extends data fusion by adding control. So what does that mean? Not only can we detect that jaywalking occurred, but now we can do something about it in real time. Now, I deliberately don't say what we do about it because we want agencies to choose what they do about it. You have access to and control of anything connected to the integrator. So you decide what to do when jaywalking is detected. For example, turn on some flashing lights, send a warning to the connected vehicle system. It's your choice. Being able to detect some condition, then provide some real-time intervention that you choose is the fundamental principle behind transportation fusion. So now that we've defined transportation fusion, let's reiterate what the integrator AI is. The integrator AI is a software solution that runs in the traffic cabinet and it orchestrates transportation fusion. Hopefully that makes a bit more sense now. Our goal is to provide a software solution at the edge that fuses control and data and lets you build real-time solutions to transportation problems. So how do we get LiDAR into the transportation space with the integrator AI? We were asked to join a project that wanted to replace existing detection system with LiDAR, but they lacked the component to actuate the signal. Luckily, this is something we already did. We already had been adding driver support for many different traffic signals as possible. For example, SDLC, NTCIP, detector racks, etc. We also already had our traffic signal fusion app developed for anticipation of actuating the signals. So we were the right product to complete their project. We added the driver to support our first perceptions partner. This driver was responsible for bringing in the object and zone information that we'll be using to determine actuations. Now, there's a lot more nuance to how this works, which includes some trade secrets, so I can't explain all the details, but now that we have our sensor input, it was only a matter of deploying. We deployed at the proposed intersection, which was quite busy, so a good test. Our interface to the traffic signal was SDLC, and we were operating as detector rack BIU number 2, so channels 17 through 32. Although we didn't initially actuate it since our BIU channels weren't mapped to anything in the controller, but you could see the calls going into the signal to verify operations. We took advantage of this position to fine-tune our algorithms and make sure everything was working to our liking. We did have some specific requests from the agency, which we also focused on. They wanted bike lanes. They had bike lanes, but no current detection system. So we were able to add the ability to actuate the signal for those lanes. They wanted bike lanes to actuate the signal for left turn lanes, which were shared with cars. Their current detection system couldn't pick up bikes. They didn't want bike actuations for through movements on the major streets, but they did want it for the minor streets. They wanted to also experiment with passive pedestrian detection. It didn't take long, but we had fulfilled all the requests and had a working solution in no time. Over time, we took feedback from the agency and continued to make improvements to the whole solution. And that leads to where we are now. We're adding more and more perception software to our support. Each of them gets access to the same features the integrator AI provides. We're still discovering new ways to leverage the detail that LiDAR provides, as you'll see in coming slides. So what are we doing now? Actuating the signal is only a small part of what we do. LiDAR has enabled us to create some novel concepts and functionality. We added support for several other devices and products. We're still adding support for more products. We want to make sure we eliminate vendor lock and to make sure that our product can benefit everyone. So we're going to keep this up for the life of the product. While observing our deployed solution, we fine-tuned our zone design. Also, we needed access to more information on traffic signals. So we improved our traffic signal interfaces to get that information. We needed a place to collect the data fusion that we were getting. So we created a special data bucket interface for that. To really open up our versatility in transportation fusion, we also created a logic wiring app, an app built to let the user craft their own transportation solutions. As we reflected on current deployments, we created the concept of object pathing, which is a simple method for determining how travelers are moving through the perception regions. Then we took advantage of the individual tracking and created the concept of object tagging, which lets us tag individual travelers under certain conditions, then have the ability to track them as they use the roadways. Then we discovered a simplistic yet sophisticated way to detect wrong-way drivers that only LiDAR enabled. To increase our data fusion support, we also added object analytics to our system, which essentially aggregated traveler information into a centralized location. Then we created our SPM Plus app, which we built on top of LiDAR to provide much better details to signal performance measures than was previously accessible before. In the next few slides, I'm going to show you how we accomplish these things. First, we expanded our support for other devices and products. We're continuing to add support for more products, and this will continue till the end of the integrator AI. If something you have isn't currently supported, we can easily add support for it. Our system was designed to expect expansion, so we designed it so our development schedule could be completed quite rapidly. To put that in perspective, adding support for perception software can be done in as little as a week or two, bearing testing, access to equipment, and cooperation of the perception vendor. Our fastest was 1 day, but don't use that as the norm because we had exceptional access and support by the vendor to do it. Next up, we fine-tuned our zone design for LiDAR. We wanted to accomplish several use cases utilizing the detail that LiDAR provides. As we figured out our needs to accomplish those use cases, we constantly redesigned the zones to support them. We're still making improvements, but so far this design has held up for quite a while now and has enabled us to do many things at the intersection. Some context, this is a 4-way intersection. There are no crosswalks here or pedestrian traffic. The agency plans on rebuilding this intersection to include crosswalks and bike lanes, which we're prepared to support. So they wanted to test out LiDAR to see how it performs and how it may help after the rebuild. It's helped us create some pretty novel use cases. Now, the agency was only asking for actuation, but you could do a whole lot more with integrator AI and LiDAR. We started adding more functionality to the site over time. As of right now, what we're doing at this site is stop bar actuation, advanced detection, providing SPM Plus analytics, providing object analytics, detecting railroad loitering, detecting railroad breakdowns, preemption logging so we know when the trains go by, detecting intersection impedances, catching and logging red light runners, catching and logging illegal movements, and lastly, wrong way driver detection. We're still discovering new use cases for the site that LiDAR enables us to accomplish. One important thing to highlight is that as we add new use cases to the site, we don't need to add any additional equipment to support them. We only add algorithms or utilize an existing transportation fusion app to accomplish them. So when we say LiDAR adds value, this is what we mean by that. It's not just a detection system for actuation. We made improvements to our traffic signal interfaces. Originally, they only actuated the signal, but we took advantage of the extra data we had access to. We did this because in order to achieve versatile transportation fusion, we needed access to more information. So we added information like timing, phases with separate vehicle and pedestrian state details, rings, ring barrier diagrams, and movement states. Now, NTCIP natively supports most of this stuff. However, SDLC doesn't. But if you look at our SDLC interfaces, like the one in the top left here, you still get all that information when you use our product. As far as we know, we're still the only ones that can actually do this purely from the SDLC interface. Although we've heard of others trying to do this, but not doing so well. Either their solution didn't work for all controllers, like ours does, or they couldn't get it to work at all. A few tried to get us to reveal how we did it, but obviously this is a trade secret of ours, so we're not going to give it to them. It's a critical feature if we're going to work with any traffic signal, though. And this lets us provide the transportation fusion that we need to accomplish all the use cases that we're looking to do. Next up, we created a transportation fusion app that we call Logic Wiring. The idea for the name was the fact that you configure your own logic and then digitally wire devices to work together. Leveraging the detail of LiDAR and the data from other devices we're connected to, this app lets agencies craft their own real-time transportation fusion solutions. It works by letting you configure a set of conditions to look for: a car going over a certain speed, catching cars moving into the intersection when they had a red light, a surge of pedestrians waiting to cross, a car too close to pedestrians, drivers going the wrong way, just to name a few. Then it lets you configure what you want to do about those conditions. You can control any device connected to the integrator, put in a call to a detector channel, modify signal timing, send out an email, trigger a relay, post a message to a DMS sign, post a message to the connected vehicle system. Any control that we provide, you can configure and execute as an action. This is a really powerful tool that lets you create all kinds of solutions to problems. Next up, we created a data bucket interface. Basically, when an event occurs, like red light running, jaywalking, or wrong way driving, we wanted the option to store this information about the event so we can study it. That's what this is. When an event occurs, we configured our wires to log this data to this bucket, where you can go back and pull up the event to see the detailed information about it. Now, what's great about this is that it provides a lot of context we didn't have access to before. For example, when someone runs a red light, you can configure it to take a snapshot of the traffic signal state and all the other travelers as well. This gives you a much better picture of what was going on when the red light running happened. Let's go through some of these events that we've captured at one of our deployments. This is a wrong way event that we logged at a four-way intersection. We configured wrong way events at this intersection to capture three things for us: details on the offending vehicle, a snapshot of the signal when it happened, and a snapshot of all the other cars and people around. Starting at the top here, we get a summary of information about the offending vehicle. We can see that it's a car was going about 20 miles an hour when it got caught doing the wrong way. We can also see towards the bottom a chronological list of zones that the car passed through. This zone list can tell us what the car had done up to when it was detected going the wrong way, including when and how fast they were going at each of the zones. Starting at the top of the zone list, we can see that the car came from the eastbound approach. This seems like this driver had drifted into the westbound approach lanes as it was departing the intersection going eastbound. Now, let's take a look at the other vehicles and what the people were doing at the intersection when this happened. Here's a snapshot of all the cars being tracked at the time of the event. From what we can tell with this information is that there were no cars on the westbound approach when this happened. So it was likely this driver was not paying attention, simply drifted into the westbound lanes while they were leaving the intersection. Below this object list, we can see a snapshot of the traffic signal state when the event happened. We captured everything we know about the signal, but what we're interested in is the state of the phases. For eastbound, that is serviced by phase 6 at the site. And if we look at phase 6, we can see that it had a green light for the last 29 seconds. We know they at least didn't run the red light when it happened. Let's examine another event. This one is a red light runner. Looks like they were heading eastbound. The last zone we recorded them in before they entered the intersection was eastbound left. This is the lane that permits a left turn or a through movement. Now, my initial guess here, judging by the fact that the driver started speeding up, is that they were trying to beat the red light. But let's look at the rest of the information we have to see if that remains true. Looks like there were a lot of vehicles at an intersection when they ran it. One curious part about this is that there was a truck still in the middle of the intersection. So I'm actually changing my theory now. I suspect that this truck was probably blocking the car's view. The truck probably accelerated so slowly that the light turned red again, and the car was following so closely that they couldn't see the light was red when they entered the intersection. So let's take a look at the state of the signal. So remember, phase 6 services the eastbound approach. So let's look at phase 6. Phase 6 was red for 7 seconds when the car entered the intersection. This truck was likely impeding the flow of traffic quite a bit for the light to be red for 6 seconds when this car entered the intersection. Likely, the truck was not paying attention and almost missed the light. By the time they started moving, the light was probably already changing to red. The car behind them was probably following too closely to see the red light, and when they entered the intersection, the light was already red. So I would consider this the fault of both the truck and the car. The truck was likely not paying attention and impeded the flow of traffic when the light turned green. Then the car was following too closely to see the light turn red. We'll just look at one more event, then we'll move on. This is a railroad loitering event. One of the approaches for this intersection has a railroad that crosses over it. It's really close to the stop bar. You could probably fit one, maybe two cars past the railroad before there's no more space left. We were curious if we could track how often people stopped on the tracks while waiting at the light. We set up this event to catch when anyone was in the area of the track for too long. I think we set it to 7 seconds. We shaped the zone as small as possible and made sure to only cover the area where a train could strike the car if they were picked up in it. What we learned is that drivers do this quite frequently at this site. They'll essentially stop on these tracks, waiting for the light, not realizing they're creating a dangerous situation. As you can see, the last zone in the list shows them in the railroad zone for 7 seconds. This means the car stopped within the zone where the train could hit them. This is obviously a dangerous situation for if the drivers can't pull up or reverse when the train does come. One thing to learn from this is that if we can detect when cars are stopped on the railroad tracks, we should also be able to detect when cars break down on them. This might lead to a safety system where we can alert railway authorities of any track impedances and prevent some pretty nasty disasters. Moving on, object pathing. This is a concept we came up with as we started working with LiDAR. It essentially refers to our ability to keep track of how objects path through a perception region. Now, LiDAR does give exact heading and trajectory information. However, that was prone to complicated configurations and a bit of ambiguity. So it wasn't a practical solution for us to look at. Instead, when we talk about tracking an object's path, we're referring to the chronological order of detection zones that the object traveled through as they moved through the intersection or roadway. This is much simpler to understand and removes that ambiguity. This opens up some pretty powerful use cases. For example, wrong way driver detection, illegal movement detection, the ability to deduce exact movements like right turns, left turns, or even U-turns, and many more. The concept is that as objects travel through the zones, we keep a history of the zones that they enter in chronological order. You can then configure our apps to look for certain zone orders in an object's path history and perform certain actions when certain patterns are detected. In this example, we have an intersection. There's a right turn only lane indicated by the 1 on top of the orange zone. Drivers were prone to going straight from this lane, even though that's not permitted. So to detect that happening, we configured one of our apps to look for them traveling from zone 1 to zone 2. If we discovered that the object path pattern of zone 1 to zone 2 was present, then we know for sure that they went straight from the right turn only lane. This is a level of detail that only LiDAR can provide us. Now, coming up in the next few slides, we have a slide that explains how we can accomplish this for wrong way detection using this concept. Before that, we need to explain one more concept: object tagging. The concept here is that since we can track individual travelers, there might be an advantage to placing tags on them under certain conditions. The tag would persist with that traveler as they move through an intersection or roadway. This would allow us to track where the driver or pedestrian went. For example, a red light running and right turners. Right turns are lawful if the driver stops first. So we look for drivers stopping in a right turn lane. If they stop, we place a stop tag on them. Then when the driver proceeds into the intersection and executes that right turn on red, we check if they have the stop tag. If they have stop tag, we know it was a lawful right turn. If they didn't, then we know they ran the red lights.